All right, so today we're going to start by looking at a perfect complements example. This is going to happen when a utility function describes a situation where two goods, being x1 and x2 in this case, are used together in a fixed proportion in order to maximize utility, hence why it is represented by the min function that we have pictured here. So first thing we can get started with before we do our ordinary demands is actually just visualize and make a graph of what this should look like. So first thing we'll do is we'll just pick a constant number. It's pretty arbitrary what you pick. I like choosing 10, but it's not really important to actually solving this. It's just more for visualization. So we're going to have two cases for when we're plotting here. So we're going to have case 1. This is going to be when 2x1 is going to be greater than 4x2. So in this case, just looking at the min function is going to take whichever one has, is worth less numerically. So in this case, our, equation tells us that the 4x2 is less, so we can just set that equal to our constant. And then we can just find that our x2 is equal to 2.5. And we're going to have a second case, which is going to be the exact opposite. This is going to be when 2x1 is actually going to be less. So in this case, we're going to select the 2x1 and set it equal to our constant and get that x1 is equal to 5. If we were going to plot this, we have x1 equals 5, and we have x2 is equal to 2.5, and a little dot here. And the bundles would fall, the optimal bundles would fall anywhere alongside these lines, right? And then we can just draw a line here, kind of showing that we'll have, if we pick different constants, it would have just fallen, higher, or it could have also fallen lower. But whichever constant you pick, it'll fall along that line where you can make the bundle. We can also just check this by, like in our min function here, when it says 2x1 and then 4x2. It's kind of like the same thing as saying 2x and then 4y. So like, if we were to set these equal to each other and make an equation, we would get y equals 1/2 of x, which would match the slope of this line here anyways. So with that being said, we're going to do what we did for the Cobb-Douglas example, where we want things in terms of x2, so that way it's going to be easier to simplify. So we're going to assume that since we're consuming in a fixed bundle, that these numbers are going to be equal to each other. For the first step of the ordinary demands. And then x2 is going to equal 1/2 of x1, which is also constant with this equation here. And then we can plug this into our budget equation, which is p1x1, p2x2, but we're going to simplify with the new x2 value we have, which is 1/2 of x1. And then if we were to write this out, it's going to give us p2x1 all over 2. And then we want to isolate x1, so we're going to remove that from both of these. And then divide it to get x1 by itself. And I personally don't like working with fractions in the denominator if possible, so we'll just simplify this and multiply everything by 2, giving us the final ordinary demand for 1 being 2m all over 2p1, and then adding p2. That's going to give us our first ordinary demand. For the second one, we have this equation here, x2 equals 1/2 of x1. So all we're going to do to find our x2 is going to be to take 1/2 and distribute that to our first ordinary demand. Doing so should give us something that looks like this. And I guess once again, we could also just simplify this and write it as just we didn't have to do all that multiplying. We could have just left it as m over 2p1 plus p2. So now that we have our two demands, we're going to look to graph the inverse demands, which is going to be just in terms of the price. So since we're doing it for good one, we're going to have P1 as our y-axis and X1 as our x-axis. So looking at our first ordinary demand here, we had X1 equals 2m all over 2P1 plus P2. Now we want to isolate P1 in this case, so that way it's independent, and then we can just start by multiplying both sides by 2P1 plus P2. And then divide. And then subtract. And then lastly, divide everything by 2. Should leave us with this being our final function in terms of x1. One thing that you will notice here is that we actually have a transformation of minus p2 over 2, which is going to shift the graph, which is why we actually do have an intersection point on the x-axis here somewhere, which is going to be the important thing for us to note. So in order to do this, if there's going to be a point on the x-axis, that means that P1 is going to be equal to 0. So we just need to find what that value is going to be when P1 equals 0. So we actually can just kind of copy this equation from down here. Equals 2m, because this will tell us what our x1 is. And so if we had P1 being equal to 0, our x1 in this case is just going to be equal to 2m over P2, giving us a point like this. And then it would curve up, and it should never touch the price axis. All right, so for the Engel curves, it's going to be the similar type of deal, except we're going to want to have our budget on the y-axis. And so our demand was 2m all over 2P1 plus P2. So here we want to have m as our isolated term that we're solving for, so similar step to earlier. And then we can just divide this whole thing by 2. And this is going to give us our function. So if we were going to like start plugging in numbers here, if we plugged in like 0, we would see that it would just give us a point here because it would set our m equal to 0. And the trend that we want to notice here is that it's going to end up being linear, with the slope being everything that the x1 is not included with. So for every one x1 that we shift over, the slope of the line is going to shift by 2p1 plus p2 all over 2. And that would just be quite simply how you draw the Engel curves. Thank you.